Alright then, so starting off from where we started from last video, where we were talking about the combustion of methane, and we balanced the equation using the linear algebra that we know, plus 2H2O. Alright, and we found that we could do this by writing a matrix that had along one edge C, H and O, and along the top was the coefficients 2, x3 and x4, and we know that matrix had to the matrix times the vector, which is this thing here, had to equal 0, and that's the mass balance that we knew of. Now, something I just want to point out is that we can have any multiple of this equation here, and it's still true. So if we had 5 times this, then that would be 5, this would be 10, this would be 5, and this would be 10, and it would still be balanced because the amount of atoms, the different atoms on the left hand side, are equal to the amount of atoms that we have on the right hand side. And so this equation is still balanced if we times it by 5. So what I'd like to do is just explain a matrix that you can have that can scale the amount or the quantity of something. So we know that the identity matrix is made up of a whole bunch of zeros. So let's say that let's just do the identity matrix for this 4x4 matrix, and 0, 0, 0, 1. Okay, now if we times this matrix by our vector here, which is going to be 1, 2, 1, 2, which is the coefficients that are usually out here. This is 1 usually, this is 2, this is 1, this is 2. Then what we're going to get out is, if we do the matrix multiplication, we've got the row, we put it down the column, we're going to get out a vector 1, 2, 1, 2. So that's great. Now let's say that if we have this matrix here, and we times it by some value. Let's say we times it by 5. So if we go 5, 0, 0, 0, 0, 5, 0, 5. And now if we times each of these values out, what we'll find is that we're going to have the same vector that comes out multiplied by a factor of 5. And so this is how I kind of want to introduce the equations, where we have a matrix over here, it operates on a vector here, and it ends up having a number here and the same vector out. And these are very, very special form of equations, and it's called an this is called an eigenvalue, so it's kind of an eigen equation. And eigen is a German word which basically means special. So these are special solutions. Now I chose this example because it's nice and easy to see that you can have infinitely many matrices that just have different numbers along the diagonal, and each of those matrices will have an associated eigenvalue, and so that's what this value is over here, and we usually denote that by the Greek symbol lambda. But you can see that as soon as I start to put cross-diagonal terms here, this won't be the case, because we're going to start to scale and we're going to start to change this variable here. And so there's only particular matrices that we're going to end up getting eigenvalues for. But this is fundamental, because when we come to solving the the equation, the Schrödinger equation for molecules, what we'll find out is that we'll have often a matrix of functions, and we'll times that by what's called our wave function, and that will give us the energy, which is just a number, which is our lambda, times the wave function again. So you can think of this as the matrix A, you can think of the wave function as the vector, and basically this is the form of the an eigen equation.
So it's really important that you can work out how to calculate the eigenvalues and the eigenvectors of a matrix that you're given.